Good afternoon, everyone. Good evening, everyone. I am Chanda Devnath, one of the PMRE Fellows of Ajar Berhampur. I am pursuing my PhD in Organic Synthesis. So, I am the TA of this course, instructed by Professor Nandita Madhavan. So, this is the extra class where I will try to give an overview of the course, which I have told in these last 8 weeks, and I'll also solve some extra questions based on that, which will give an idea how to solve questions. Okay, let's start. So in the very first class we started with aromaticity. So which are aromatic compounds? The compounds following these 4 rules stated by Huckel are called aromatic compound. First one is planar, second fully conjugated, third monocyclic system, and the fourth is 4n plus 2 pi electronic system. So here we have shown some of the example. In the first one, its number of pi electron is 8 pi. So it will be a non-aromatic. Here number of electron is 4 pi. So it's a anti-aromatic. It's 2 pi. So it's aromatic because it's following the 4n plus 2 rule. Here it is 6 pi. This is also aromatic. This is our known compound benzene. Here it is 6 pi. So this is aromatic. Each pi bond means 2 electron. So each pi bond means 2 electron. That means 6 pi bond means 3 pi bond means 6 pi electron. Okay. Here, like we solve this. Now talk about this type of system, which are this cis aniline. It has 4n plus 2 rule because it has 10 pi electron. So it is a 4n, follows the 4n plus 2 rule. But due to cis structure, due to this cis conformation of this all the double bond, this compound is not planar. This compound is not planar. So that's why it's not aromatic. It's not aromatic. Whereas in this compound, when there are some bonds are trans and some bonds are cis, in that case it can create a planar structure. Therefore it is aromatic with a 1, 2, 3, 4, 5, 6, 7, 8, 9, 18 pi electron. 18 pi electron. If n equals to 4, then this rule satisfies. It has 18 pi electron. Okay, so aromaticity is clear. Then we started discussing about resonance and hyperconjugation. So what is resonance? Resonance is the stabilizing of a molecule through delocalization of the bonding electron in the pi orbital. The most stable form of a molecule is that show all the possible structure a particular molecule can have. Resonance structures have the same number of electrons and molecular formula. The hybridization of the atoms in the molecule should be the same. After resonance or during the resonance, the hybridization of the all the molecule should be same before and after the resonance. So here I have shown some of the example. Here we have taken phenol. Phenol of oxygen can take place in a resonance with this benzene ring and forming this 4 resonating structure. In all the cases, the hybridization of all the bonds are same. Okay, all the carbons are sp2 hybridized, whereas this oxygen is sp3 hybridized. This oxygen is sp3 hybridized. In this case also we have got 2 resonating structure for acetic acetate anion. Then we talked about hyperconjugation. What is hyperconjugation? The non-bonding resonance of the CH bond. If suppose this type of system is there, there are H. This H involved in resonance with this double bond. This type of non-bonding resonance is called hyperconjugative structure. Okay, this is called hyperconjugation. Any double bond having highest number of alpha hydrogen, that means it will have highest number of hyperconjugative structure, and that will be highest. That will get high stability among the other double bonds. If you want to know more about this, you can go and check my video on this. I think I have taught this concept in the very first class. The video is already in the YouTube. You can go and check, where I have discussed about the resonance and hyperconjugation elaborately. I have also discussed some of the examples based on this, which will give you a better idea of this concept. Next, we started discussing about reaction mechanism. So there are three types of reaction mechanism. First one is polar, second radical, and third is concerted. So in this case we are mainly focused on the polar type of reaction. So there are different type of polar reaction. First one is substitution. First is substitution, second is elimination, then addition, elimination, and elimination addition. So substitutions are two types. First is nucleophilic and electrophilic. Nucleophilic substitution, again there are two types, SN1 and SN2. Mainly two types. There are some other types also, but mainly two types, that is SN1 and SN2. Electrophilic substitution also divided into mainly two types, aromatic and aliphatic. Eliminations are also exist in a two way. One is syn elimination, where the eliminating two groups are seen to each other. Another is anti elimination, where the eliminating groups are anti to each other. The anti elimination can be divided into three types. First one is E1, then E1CV, and last one is E2. In the next classes we discuss about each of them. If you want to know elaborately of each of these different type of substitution and elimination process, you should go and check those videos. I am giving a brief, where when SN1 means when the substrate leaves the leaving group first, forming a carbocation intermediate. After that, nucleophile attacks, and we get our substituted compound. Whereas in case of SN2, what happens in case of SN2? In case of SN2, the nucleophile attacks and remove the leaving group, and the reaction goes through a penta-coordinated transition step. our desired product. Okay. The next is aromatic substitution and aliphatic substitution. You can go and check those videos. Next, then we talked about addition reaction. The E1, where E1 is similar to SN1, where the leaving group leaves first the system, then elimination takes place, and E1CB. Then the last one is E2. E2 is also similar to the SN2, where the H elimination takes place at the single step. For this E2 elimination, an anti-periplanar arrangement is highly required to eliminate the leaving group from the system. After discussing different type of reaction mechanism, we focused on describing different type of postulate to get an idea that if any unknown reaction is given, which type of mechanism it is following. To get an idea of that, there are some postulates are given. First one is Hammond postulate. So according to Hammond postulate, for exothermic reaction, the transition state is closer energy to the reactant. Therefore, the transition state structure of the can assume to resemble more with the reactant, and as well as in case of endothermic reaction, the transition state energy is closer to the product. That's why the structure of the transition state can be assumed to resemble the product more than the reactant. Here is the graph is given, where the transition state in case of exothermic reaction, the transition state is closer to the reactant and it has more reactant character in itself, and in this case the transition state is more closer to the product, so it has more product character in itself. Okay. Next we talked about, then after describing Hammond principle by different type of example, we move to Hammett principle. So what is Hammett principle? Hammett principle used for the benzoic acid deprotonation reaction to determine the substituent parameter sigma x. In this case, by increasing the electronegativity of this X group, the rate of the reaction enhances, and by taking log Kx by Kh, we get the sigma value. When Hammett tried with different type of substituent, for electron withdrawing substituent, the reaction is more feasible to the right hand side, giving a high K value, while with electron donating group, they give a very low K value, whereas the sigma is less than 0. So what is there is according to Hammond rule, log K by K0 equals to rho sigma. When rho is greater than 1, the reaction is more sensitive than that of the benzoic acid, and negative charge is built during the reaction. When it is less than 1 but greater than 0, that means it has less sensitive to the substituent than that of the benzoic acid, and a negative charge intermediate has been formed. When rho equal to 0, it has no effect of substituent in the reaction. When rho is greater than 0, when rho is less than 0, that is negative, that means a positively charged intermediate has been formed. This is the significance of rho. If any reaction rho value is given, from this value or charge we can get an idea that the reaction is going through which type of intermediate. Further, we will discuss about some of the question where you can see that rho value is given, and from the rho value you can get an idea of the intermediate involved in the reaction medium. Then we talked about the solvent effect of for SN1 and SN2 type of reaction. In case of SN1 reaction, SN1 reaction, the due to generation of charged species, the intermediate get more stability than that of the substrate, whereas in case of SN2, due to the substrate gets more stability than that of the intermediate. That's why in case of polar solvent, the activation energy decreases, but in case of SN2, while using polar solvent, the activation energy increases because our reactant gets more stability. Here you can see in case of SN1 type of reaction, the intermediate and the transition get more stability than that of the reactant. Reactant has its same space, that's why the activation energy decreases and reaction rate increases in presence of polar solvent. So SN1 polar solvent favors because it stabilizes the positively charged intermediate, and intermediate stability is the controlling factor in this reaction. Favors the SN1, while in case of polar solvent in SN2, the substrate gets more stability than that of the transition state. Substrate gets more stability. Because of this, the activation energy enhances. Therefore, the polar here, the non-polar solvent favors the SN2 pathway. Suppose a reaction is given like this one. Suppose this reaction is given. So now this is secondary. So this type of reaction, when ethanol is used as a solvent, in that case reaction goes through a SN1 pathway. But when any non-polar solvent is used, like lithium, in that case reaction goes to SN2 pathway. Okay, understood? Then after solving the solvent's effect on the reaction, we move to discussing primary kinetic isotopy. What is that? Primary kinetic isotopy may be found when a bond to the isotopically labeled atom is formed or broken. In case of primary kinetic isotope effect, the rate, while if we substitute a hydrogen bond, CH bond with a CD bond, the rate of, due to greater bond strength of the CD bond, it will need greater amount of energy and time to break, and it will react in a slower rate than that of CH. Therefore, KH will be greater than KD. If KH is greater than KD, it will show a primary kinetic isotope effect. If the CH bond is broken at the rate determining step, and by changing the CH bond with the CD bond, the rate get affected and the rate get slower, then the reaction, then it will show a primary kinetic isotope effect. Next is Secondary kinetic isotope effect. The secondary kinetic isotope effect is observed when no bond to the isotopically labeled atom in the reactant is broken or formed. The secondary kinetic isotope effect is observed when no bond to the isotopically labeled atom in the reactant is broken or formed. That means when isotopic substitution at the alpha or beta position of the bond is broken, that is not broken in the bond which is involved in the rate determining cell, that is not the CH bond, but the CH bond is getting broken at the alpha or beta position of the bond breaking at the RTS. Next is steric effect on the bending vibration at the CH bond is longer than the CD bond. Normally, if it is show a normal secondary kinetic isotope effect, if any compound changes hybridization from sp3 to sp2, it will show a normal secondary kinetic isotope effect. But if the hybridization changes in a reverse way, that sp2 to sp3, then it will show inverse secondary kinetic isotope effect. What is in normal kinetic isotope effect? That means Kh by Kd equals to positive, and if it is negative, then it will show inverse secondary kinetic isotope effect. Next is isotope labeling. Labeling a particular position in the reactant to determine the mechanism is called isotope labeling or isotope scrambling. To know the reaction mechanism, we can label one of the atom involved in the reaction of the substrate by its isotope. Like suppose if we mark the carbon with its C13, then after the reaction, if C13 is still present in the reaction, the place of from the C13 place of the C13, you can determine the mechanism of the reaction. Here you can see we have marked the carbon of the carbonyl group with the C13. Then when you perform the reaction, after the reaction, one of the carboxyl group contains the C13 carbon. From there we can get an idea that the reaction goes through one of the mechanism A or B, because both of them giving a same product. Next, we discuss about trapping of reaction intermediate to understand the mechanism. So for this process we can trap different type of intermediate like anion, cation and radical. To trap an anion, we need a cationic trapping species, that is electrophilic species. To trap a cation, we need anionic or nucleophilic species. To trap a radical, usually nitron or TEMCO, TPPA, different type of reagents have been used, which are stable radical and can be stored in laboratory. This type of radical trapping reagent, when added in the Combs reaction, it will trap our generated radical, which will prove that and suppress the reaction and giving a expected product and giving a trapped product intermediate. So how we know that in a reaction benzene intermediate is forming? So benzene is a highly reactive intermediate. Right now recently the benzene chemistry has been very famous. Some scientists are recently working on this chemistry. So benzene is a highly reactive intermediate with a distinctive structure featuring a benzene ring with a triple bond. Is crucial in nucleophilic aromatic substitution and Diels-Alder reaction. Understanding the benzene's reactivity aids in synthesizing complex organic compounds and offers educational insights into the reaction mechanism. So how these benzynes can be formed? Is another possibility. Where if we are forming a Grignard moiety, then this negative Grignard has a partial negative charge as this carbon. So this negative charge will come here and remove the fluorine from the system. We can get a benzyne. Then just by coupling to alkyne with the alkyne system, we can get this benzyne compound. There is another different type of possibility by which we can form this benzyne. Here I have shown all of them. This is another one which I showed just recently. There is another probability just by if it comes here and this N2 will remove from the system. There are some different probabilities there. If OTFs comes here, in this different pathway you can form benzyne in our reaction mixture. Now, how you can get an idea that benzyne is forming? Just by trapping it. Now suppose this type of reaction is given. Just by adding HONO, we know that what it will form? It will form a diazo compound. NNO2HCl will form a diazotization of this amine. This is a diazotization reagent that we know, I think you have learned about in your preliminary classes. This is a diazotization reagent. So whenever there is a diazotization reagent is given and a primary amine is there, it will form a diazo compound. So it will form now here you can see a diazo compound with a carboxylic acid adjacent to that form a benzyne. So here similar type of reaction will take place. So this comes here. This gets removed from the system, forming a benzyne intermediate. Now to trap this benzyne intermediate, this can act as a, in the previous slide we discussed that it acts as a very good dienophile for Diels-Alder reaction. So there is a diene in your system. Inside the system there is a diene. Inside our system there is a diene. So this diene will undergo the Diels-Alder type of reaction, giving us our desired product. Okay? Understood? I hope it's clear. Let's go to our next question. So here also they have given a diazotization reaction. So what will form? It will form diazo compound. This will comes here. Forming benzene. Now this benzene will react with one of these double bonds. So suppose if this is already aromatic, so this will not react. Now if among these two diene, one of them will react. Now suppose if this one reacts, there is a double bond comes here. There is a quality double bond comes here. Sorry, this one is the quality of double bond coming here. So that will not give any extra stability to the compound. But these two double bond react, then it will give a double bond at this place. Just imagine Diels-Alder reaction. Whenever this diene reacts, there is a double bond comes at this place. So this giving a extra stability to this ring, because this ring is gaining aromaticity. So this ring is getting aromatic nature. So this will react to this diene. So among these three rings, the middle diene will react desired product is so there will be double bond at this place. From these two center, another double benzene, that is phenyl ring, will be connected. So here, if we try to draw which are the new bond formed in this reaction, so this is the new bond formed, and these two sigma bonds are new. These two sigma bonds are new, and this pi bond is new. Okay. So just by adding this type of trapping reagent, you can trap the benzene. So here is another. So if we are adding a base in this type of moiety, what will form? There is a hydrogen is available. So this NH2 will take this hydrogen, and this will comes here. Remove from the system, forming this benzene. Now to trap this benzene, what we can add? There is already living a nucleophile present in the system. So this nucleophile can attack from this place or this place. So if we attack from this place, it will open and give a negative charge at this adjacent to the OMe2. first case, what you would get? You would get this one as a product. Now, in the first case, the negative charge is adjacent to OMe group. Now, OMe has a minus I effect. OMe has a minus I effect. So, it can stabilize this negative charge, whereas it is far from the OMe. Minus I effect is dependent on the distance. So, here as it is far, so it will be less effective. So, here the product will be this one. So, this intermediate is more stable, and if you are adding H plus, it will be take H plus from amine, ammonia, and it form our 2 amino and anisole. This will be our desired product. Okay. Okay. I hope it's clear. Next. So next topic we'll discuss about is types of catalysis. So there are different type of catalysis. Like next is enzyme catalysis. So this is the basic concept we get idea when we learn about catalysis. So we learn from the nature. Whatever we have learned, we try to mimic the nature. This is the first thing when people know about catalysis. The first thing which is the application of this is the enzyme catalysis in our biological system. So enzyme acts as a catalyst for any reaction in our body or any circumstances. In case of any biological species or in our nature, to happen any reaction in our body or any human body or any living beings, to accelerate the rate of the reaction, we need enzyme. So enzyme catalysis increase in the rate of the reaction process by an enzyme, a biological molecule. Most of the enzymes are protein, and most such processes are chemical reaction. Within the enzyme, generally catalysis occurs at a localized state and called the active state. So in case of enzyme, there is a active state, the specific state is there. So it react for a specific substrate. So see, it has this type of shape. So it will just react with the substrate having this type of shape, and it will go and fit into this shape and undergoes a catalysis, forming the product. After the product formation, this enzyme will remove this product from the system, and we get our desired product. So what is the role of this enzyme here? So enzyme is trapping our substrate, and it's helping to trapping our substrate and helping it to react, and after that when it becomes the product, it removes from the system, generating the enzyme back. What do you get in case of catalysis also? Catalysis comes in a reaction, take both the substrate in closer contact and reduce the energy of the activation state, and just after the formation of the product, it gets removed from the reaction and try to activate another molecule of the substrate, and these cycles goes on. Okay. And in case of specifically, it is not for another simple catalysis, but in case of enzyme catalysis, there is a specific active site where it can involve in a reaction, because if this enzyme want to react, it can't react from this place, it has to be from this place. So for enzyme, this is specific criteria. It has a specific site that is called active site. So the another type of catalysis is phase transfer catalysis. This is one of the important catalysis right now, because we all the chemist and scientists trying to focus on the green chemistry, which is that we are trying to avoid the use of organic or the immiscible solvent which are harmful for the nature. So we are trying to perform a reaction in water medium in a greater extent. So suppose now a reaction is not, a compound is not soluble in water. How can you take him into the water and make him react with our substrate? So it's possible if our reagent is, suppose our reagent is soluble in water but our substrate does not. So you have to take them, both them closer into the same medium so that it will react. Otherwise both of them will be in the different phase. They will not come closer to react. In that case we need this catalyst, that is called phase transfer catalyst. In presence of this catalyst, the compound which is not soluble in another type of solvent, or the compound which is not soluble in aqueous phase or water phase, it make it soluble into the aqueous phase, or a part of it make it soluble to the in the aqueous phase, and let it react and give us our desired product. This is the one of the important type of catalysis in the modern chemistry, because in presence of this catalyst we can perform a reaction very easily, irrespective of our substrate and product. Our substrate and reagent are miscible in the same solvent. So in a phase transfer catalyst is a catalyst that facilitate the transition state of a reactant from one phase into another phase where the reaction occurs. Phase transfer catalysis is a special form of catalysis and can act through a homogeneous or a heterogeneous catalysis method depending on the catalyst used. Ionic reactant are often soluble in aqueous phase but insoluble in organic phase, and in absence of phase transfer catalysis. Suppose a reagent, some salt is there, that will be soluble in aqueous phase, not in organic phase. The catalyst functions like a detergent or the solubilizing the salts into the organic phase. The phase transfer catalyst refers to the acceleration of the reaction upon the addition of the phase transfer catalyst. So here you can see in this diagram what is happening. In this diagram what's happening? In this case, the quaternary ammonium salt is soluble in water, whereas the NaCl is also soluble in water. But here in this case, when this RCl comes in contact by this interface, it reacts with the substrate and forming RCN and Q plus C, where there is a transfer from Cn to this R in presence of this quaternary, this phase transfer catalyst. This phase transfer catalyst helping him to react and forming this type of substrate where the NaCl is dissolved in water and RCl is soluble in aqueous solvent, but they react forming our desired product. Okay. So let's solve one of the question. So which crown ether is needed to achieve the following transformation? So crown ether is one of the important phase transfer catalyst where it's a cyclic ether. It can trap a cation depending on the size of the pore. If the crown ether size, the pore size is bigger, then it can trap a bigger cation like cesium. If the size is smaller, it can trap a smaller cation, that is sodium, potassium. So here they have given NaCN. So the cation is Na plus. there is a correct order. There is three types of brown ether. First one is twelve count 4, that can 12 count 4, 15 count 5 and 18 count 6. So 12 count 4 usually can trap the lithium plus, 5 count 5 can trap sodium plus, and 6 count 18 is a bigger size, so it can trap the potassium plus. So therefore our desired substrate intermediate has this Na plus as a cationic cation, so that's why we have to use this 15 round 5 to trap this and react in the system. Okay, so thank you everyone. This much for today's class. Tomorrow there is an extra class. There we will discuss about different type of question based on this chapter. If you guys are interested, can come and attend tomorrow's class. And if these classes are interesting to you, there are some previous classes which have been uploaded in YouTube. You can go and check those videos. I hope they can help. There we have discussed different type of questions, and tomorrow we will also discuss different type of questions and extra questions on this topic. Okay, thank you everyone. Have a nice day. Then we started discussing about different type of catalysis, like acid-base catalysis, binding, electrophilic catalysis, nucleophilic catalysis, strain and distortion, covalent catalysis, and phase transfer catalysis. Based on that, now we will solve different type of question. I will giving 1 minute time. Just try to solve this one, then we will solve together. So what they ask suggest the mechanism for the following reaction, commenting on your choice of SN1 and SN2. So which of the reaction will go through SN1 and which of the reaction will go through SN2 pathway, that we have to discuss. Just take a minute and try to solve this. I just give the 1 minute. Let's solve together. So in this case, the first one, what will happen? So this is a a very good living group, and this is a 1 degree carbon. So the reaction will go through SN2 pathway. Reaction will go through SN2 pathway. That's why this S minus will attack to the methyl center and will remove the system and will get our desired product. The next one, this is a 3 degree carbon, and it's an acid. So this can take a proton from this acid and turn into a good living group OH2 plus. OH2 plus, then it gets removed from the system, generating this 3 degree carbocation. Then another molecule of alcohol will attack, forming this ether complex. Okay, it was easy. The first one will go through a SN2 pathway and second one will go through a SN1 pathway. Let's solve our next question. Here also they have asked it will go through SN, which one of the reaction will go through SN1 and which will go through SN2 pathway. Just try one by one, then we will solve it one by one. I will just give 2 minutes. Just take a look and give a shot. I'll just give 2 minutes. Let's solve it. What is happening in the first reaction? You can see in this case this position is 3 degree, favoring SN1, and this position is favoring SN1, whereas this position is just adjacent to the carbonyl, which also favors the SN2. So which will follow by this reaction? So it has been seen from the result that there is an inversion has been observed. From that one we can get an idea that reaction is going through a SN2 pathway where this azide anion will attack to the center and remove this bromine, and we get this as our product. In the second one, what is happening? So this is 5-member ring, but here you can see there is a formation of 6-member ring. How is this possible? So if this oxygen attacks to this position, so this is a bad leaving group, so it will take up this proton and turn into a good leaving group. After that, this OH will come and attack to this place, and we get our desired product. Okay. Just try to note the mechanisms along with me so that it will be easier for you, because until you will draw it by your hand, it will not be remembered by you. So try to solve it. What is the next question? The next one, they have given this substrate, and while using this anionic nucleophile, they found the attacks from the below the plane, where by using this alcohol, propanol alcohol, they got a syn to the methyl, they syn attack to the methyl. So how is this possible? This is possible because in this case a SN2 pathway has been where this nucleophile attacks from the opposite plane of this epoxide, So this is going through a SN2 pathway, whereas in this case the reaction is going through a SN1 pathway. It first opens part and generating a carbocationic center, and after generating it's creating protonated, and by opening from this side it generating a 3-degree carbocationic center at this position, while this propanol attack here, and we get our desired product. This is the mechanism where here I have shown the mechanism of this. This is the mechanism of this one. So the SN2 is here, it will just attack. In case of SN1, it will get protonated and opens up to generate a carbocation at this position. Then propanol will attack from the opposite plane, because OH is already above the plane, so it's coming from the opposite plane. From the opposite plane, giving us our desired product. Okay. Note everything. Next question. Suggest a mechanism for this elimination, and why does the first give a mixture and the second a single product? Try to solve. I just give 1 minute, then I will solve it. solve this one. This is the acid which is given. So what will happen? It will get protonated first from this acid, generating a carbocation intermediate. Now there are two possibilities. There are two H's there. One is here, another is here. So there are two possibilities of this elimination process. So one will be this one. So this is called set J product. This is called complement. Both, so due to availability of two types of hydrogen, both product will be found here, and among these two, as the set J product is the more substituted one, so it will be more stable one, so it will form in a majority. Here you can see what I have shown. In the second one, after protonation of the OH, we get the radical where there is only single possibility of elimination because there is no CH is available at this position. As there is no CH is available at this position, because of that there is only CH is there, that is at this position. Therefore, there is only possibility of formation of carbocation is this one. Here you can see after elimination the similar type of process will repeat. After this, another molecule of oxygen, water will get removed, in a similar way. Get this diene as the sole product. Okay. Let's go to our next question. So we have talked about different type of catalysis. So one type of catalysis is nucleophilic catalysis. So here is the one of the example. I have told in the last class that try to go and check what is the mechanism of this one and what is the role of DMAP at this reaction. So here is the formula where this OH group will at first attack to the DCC because OH is a bad leaving group. So OH group will deprotonate this acid and this oxygen will attack to this DCC and forming this intermediate. After that, this intermediate get protonated again and alcohol will attack here and remove the system from the and we get our esterylate product. In this case, after the formation of this step, DMAP can also attack to this, making this to enhance the nucleophilicity of the reaction. So DMAP nitrogen will attack to the center, removing this from the system, generating this intermediate. This imine intermediate. Where the nitrogen is positively charged, because of that it is a very good leaving group. It's act as a good leaving group. step. Okay, I think it's clear. So here the DMAP is acting as a catalyst. Which type of catalyst? The DMAP is acting as a nucleophilic catalyst. The DMAP is acting as a nucleophilic catalyst. This is acting as a nucleophile and enhancing the Lewin group property of the substrate. So this is a nucleophilic catalyst. This is a nucleophilic catalyst. Okay, I think it's clear. Then we talked about radical reaction and how to trap it. So one of the famous type of radical reaction is this one, where this we have discussed earlier also. Hello. এই বসে আছি রুটি আর চানা মশলা না না খেয়ে ভাত ডাল ভাজা কোনো খবর নেই ঠিক আছে So this is the one of the famous type of radical type of reaction where this AIBA generates this type of radical through homolytic coupling, homolytic cleavage, and that will generate Bu3SN dot which removes the radical from this center and adding from this center and generating this radical. After that, this radical, after the formation of this radical, after formation of this radical, it will attack to this center, opening up, and we get our desired product. Now you all know that is the radical always a chain addition will take place. So it will be one of the product from A and B. 5-member ring formation is always favorable over 6-member ring. So our desired product will be option B. Next question they ask, explain the difference between the Hammett row values by the mechanism for the two reaction. In both cases, the ring marked with the X substituent, and when the X, now when the R equals to H, we get a small rho negative value, but when R equals to phenyl, we get a high large negative value. So what will be the mechanism? Now from the mechanism, rho value is negative, so it will be a positively charged intermediate is involved. That if it is highly negative, that means a positively charged intermediate is involved. Means a positively charged intermediate is involved, but a lower rho value means there is no such positively charged, but there is a probability that a partial positively charged intermediate is forming. So to support that, we found that in the first case when R equals to H, the reaction is going through a SN2 pathway. Because of that, where it is a partial positive delta positive charge is there, which is getting attacked by the external nucleophile and giving us our desired product. Whereas when phenyl R equals to phenyl, it gives a high negative value, which means there is a formation of carbocation by elimination of the chlorine, which is the rate determinants and generate this carbocation. After the attack of this alcohol, we get our desired product. So when R equals to H, the reaction is going through SN2 pathway, but when R equals to phenyl, the reaction is going through a SN1 pathway. Maybe it's here, just take a note. Next, we discussed about hydrolysis of ester. So ester hydrolysis can be catalyzed by acid and base both. The reaction goes through these two mechanisms. When it is acid catalyzed ester hydrolysis, the O group first get acidified. After that, then a water molecule will attack to this carbonyl center, opening this one. Then another molecule. Then through the proton transfer, it generates this intermediate. After that, this another molecule of OR gets protonated, and through removal of this OR, we get our desired carboxylic acid. But in case of base catalysis, the OH minus directly attacks to this carbonyl center and opens this O minus. Again, through removal of this OR, we get our desired acid. Okay, so this type of reaction can be catalyzed by acid and base both. Based on that, one question came in GATE 2018. They have asked to find the major product formed in the following reaction sequence. They have given this substrate and given acid and BH3. So by addition, by giving the acid, one of the ester group will be hydrolyzed. So this is a alpha beta unsaturated ester, whereas this is a simple ester. So obviously, when this is a simple ester, the electrophilicity is high. So better electrophile. Because of that, it will get reduced at a faster rate, giving after the reaction quantity will give CO2H. After that, they have added BH3. Now, if we go through the enolate chapter of the Caruthers, the first chapter of the Caruthers book, you can know the different type of reducing reagent and its selectivity. So suppose if any reaction in substrate contains an acid and an ester group and BH3 is added, in that case BH3 specifically reduce the acid group over the ester. So in that case, which one will get reduced? This group will get reduced. So what will be our desired product? Our desired product will be product A. Because here you can see it one equivalent of this is used, and it will then selectively reduce the acid and we get our desired product A. Okay. So I hope it's clear. So thank you everyone. This is a overview of today's class where I have discussed the total of this last 8-week session and different type of topics we have discussed in these 8 weeks. If it's helpful for you, go and check the other videos which have been uploaded in YouTube, and also I will upload the slides also where you can solve this question by yourself again, which will give you an idea how to approach the questions. and how to get an idea from the row values. Thank you everyone. Have a nice day. Thank you.